Okay, Chapter 9, the development of probability theory is the subject of this chapter, and in particular we're going to take a look at three principal characters who were instrumental to the development of probability theory in mathematics: Blaise Pascal, James Bernoulli, and Pierre Laplace. I want to talk to you a little bit about the origins of probability theory today, and then about the first character that certainly played a large role in the development of probability theory, Blaise Pascal. So let's talk a little bit about the origins of probability theory before we dive in on Pascal. Historically, probability theory arose from mathematical investigation around two real-world phenomena. I'd ask you to just take a second and think to yourself, what real-world phenomena might have motivated the origin of the mathematical study of this area. Well, hopefully you came up with this first one. It seems quite obvious that solutions to wagering problems associated with games of chance might be one place where probability theory would have emerged, as knowing the mathematics behind certain probabilistic games would give the player an advantage in betting scenarios. But the second area is somewhat surprising, the processing of statistical data for such matters as insurance rates and mortality tables. These things start to emerge in the late 1500s and early 1600s. Perhaps not surprisingly, they coincide with the age of discovery, when we place large monetary, investments into ships on the ocean carrying certain goods, and we're worried about them perhaps perishing in storms. And so the insurance industry as we know it was basically birthed at about the same time as statistical, the origins of probability theory. You can read a lot about that in our text as well, and I think it's definitely worth your read. So just a few historical anecdotes to give, some evidence of the two statements that were made in the previous slide. Cardan in 1663 has this quote: "If I'm able to throw 1, 3, or 5 as 2, 4, 6, the wagers are therefore laid in accordance with this equality if the die is honest, and if not, they're made so much the larger or smaller in proportion to the departure from true equality." So I think what we can see in the quote is that Cardan's starting to get a sense for what's going on when we throw a six-sided die. If it's truly fair, then a 1, 3, or 5 would be just as likely to occur as, say, a 2, 4, 6. So if we were to sort of investigate whether an even or an odd number is more likely to be rolled, he would argue that they're about the same, just so long as the die is honest, what we would say today as fair. And if the die is not honest, then of course one of those or multiple of those outcomes would be made so much the larger or smaller in proportion to the departure from true equality. So equally likely and not equally likely scenarios being investigated by Cardan in this quote. And then a little bit of an interesting table that was developed in 1662 by Grant, and it's a famous table because it's kind of the first time we see statisticians taking into account the idea of probabilistic distributions. What Gahn has done is, on the basis of health records, compiled a survivor distribution, and as you can see in 1662 things were not like they are today. If we have 100 survivors at the age of 0, so if we start out with a population of 100 people, then the age of the number of survivors at age 6 is down to 64. By 16 we're down to just 40, and by 26 we have 25 out of 100 surviving, 16 out of 100 at 36, and so on. Certainly a different scenario than what we would see today. It would be interesting to know what the survivor distribution, such as Grant generated in 1662, how that compared to the modern era. But certainly with the rise of medicine, we would think that this table would have a much different look today. You can see, though, that the origins of statistics here and probability of survival certainly is tied to this idea of life expectancy, and perhaps something of interest to those who are developing an industry that we today call insurance. So let's dive in with Blaise Pascal. Blaise Pascal lived from 1623 to 1662. He was a versatile scholar, a gifted writer. He was a religious philosopher, but he was also an innovative mathematician and an experimental physicist. It's notable to our discussion in the history of math is that he made huge contributions to projective geometry at a very young age. As early as 14, he was investigating conics and projections of conics and visiting with faculty at the local university. He devoted his efforts towards developing the first mechanical calculating machine in 1642 that did simple arithmetic. So certainly was interested in this idea of a calculator at a very early age in history. Then one of the curves that was certainly something of intense investigation during Pascal's lifetime was that of the cycloid. So this is the curve that we can kind of think of as generated by a point on a wheel as it moves along the x-axis. And he certainly was interested in the cycloid as well as areas under the cycloid. But in 1654, through correspondence with Fermat, Blaise Pascal initiates the study of probability. Some say it's the birth of probability. And also in 1654, he writes a treatise on the triangle that now bears its name, Pascal's triangle. What makes that significant is not so much that he was the discoverer of the triangle, it was well known to those who went before him, but rather that it's the first exhaustive treatment of the triangle in terms of studying its properties. And we'll take a look at both of these last two bullets. So let's take a look at the birth of probability theory, or what some would argue is the birth of probability theory. And it centers around a problem that was presented to Pascal by Chevalier de Mere. And he reaches out to Fermat on July 29 to 1654 to invite Fermat into an investigation of de Mere's claims. So here's what the quote is as he writes to Fermat in the summer of 1654. The Chevalier de Mere said to me that he found a falsehood in the theory of numbers for the following reason. If one wants to throw a 6 with a single die, there's an advantage in undertaking to do it in 4 throws, as the odds are 671 to 625. If one throws 2 6s with a pair die, there is a disadvantage in having only 24 throws. However, 24 to 36, which is the number of cases for 2 dice, is as 4 to 6, which is the number of cases on 1 die. And this is the great, quote, scandal, end quote, which makes him proclaim loftily that the theorems are not constant and arithmetic is self-contradictory. So kind of an encrypting, I guess a cryptic message, but let's see if we can unpack its contents and try to understand just what Pascal and Fermat were puzzling about. Let's go ahead and switch over to desktop here and talk a little bit about what is actually going on. Okay, well, let's think first of all, there are kind of two cases here. So the two settings, I guess, that they're discussing. So in the first setting, we have, I guess, this 1 die, and we want 6 to appear, and we are told that 4 rolls leads to advantage. So what does he mean by advantage? Advantage, well, I think what we mean here is in a betting scenario that if you roll a die 4 times, a 6 is more likely to appear than not. So I guess in modern terms what we're talking about is a probability greater than a half. And in setting 2, we are told that there are 2 die, or 2 dice. We want a 6, 6 to appear, and what he notes is that that if we roll the die 24 times, or the pair of die 24 times, it leads to a disadvantage. So in other words, the probability is, excuse me, less than a half. You're still not likely to see a pair of 6, at least in a 50-50 sense, in 24 rolls. So the probability here is less than a half. And I guess the thing that he notes here is that for each die in setting 1, or each roll in setting 1, there are 6 outcomes per roll. And in setting 2, there are 36 outcomes per roll. And I guess the problem that he has, or that Chevalier de Mere has, is that if we sort of think about the number of rolls and the number of outcomes per roll, it kind of seems like, well, if this is, 4 rolls and 6 outcomes, and this is, I guess, 36 outcomes, and we need 24 rolls, or we're looking at 24 rolls and 36 outcomes. The problem for de Mere is that why shouldn't both of these lead to advantage? So I guess the question is that since the ratio of rolls to outcomes is the same, why isn't advantage / disadvantage the same? And certainly seems like somewhat of a conundrum. You can think that you can see that there's some ratios that are being applied to certain settings. So to the two settings, and it kind of seems like, well, there is something strange going on. If this is a disadvantage, I mean, a bet you shouldn't take, and this is a bet you should take, then where's the difference? And how can we really explain this mathematically? So let's go ahead and sort of retrace the steps of Pascal and take a look at both settings and their true probabilities. So setting number 1, what we can kind of think of is that we have an event here, and the event is 6 appears at least once in 4 rolls of a fair 6-sided die. And the way that Pascal approaches this is he identifies the complement of that event, which we'll use I guess the exponentiated c for complement. So the complement would be the opposite of this event. So if a 6 appears at least once in 4 rolls, then the opposite would be 6 does not appear at least, I guess at all, does not appear in 4 rolls. And he goes after the complement's probability and uses the complement rule. If we kind of think of it this way, the probability of an event is equal to 1 minus the probability of its complement, common rule, that complement rule from probability theory. Then if we know the probability of the complement, we can subtract it from the total probability of 1 and find the probability of the event itself. So let's talk about the probability of the complement. Well, the probability of the event's complement here, we know that for each roll, the probability that a 6 doesn't appear is 5 out of 6. If each of these rolls are independent, then 5, 6 times 5, 6 times 5, 6 times 5, 6, using the multiplication rule for independent events, that will be the probability of the event's complement, so 5/6 to the 4th. And we can then calculate the probability of the event as 1 minus 5/6 to the 4th, which will be 1 minus 625 out of 1296. That's 671 out of 1296. And indeed, we can see that it is advantageous in these 4 rolls where more than half of, I guess the probability is more than 1/2. This is definitely greater than half. And the other thing you can notice is that Chevalier-Demer does have the true probability correct, that 671 out of 1296 as a probability is equivalent to the stated odds. I guess I'll just sort of put it up here. The odds that were stated were what, 671 to 625. So ways that it can occur, ways that it cannot occur. So the sum there is your denominator here. And so certainly it seems like Chevalier-Demer does have Chevalier-Demer does have the right idea for the first setting. And so let's take a look at the second setting and see if indeed the probability is less than a half that a pair 6 appears in 24 rolls. And you can imagine that this is very similar to setting 1. I guess I can leave this next door so we can kind of watch it. So in setting 2, we simply have, I don't know, it's, something really similar. The only difference would be that the probability of a 6 not appearing, let's just go ahead and march through it. Let's let A be the event, and that 6,6 appears at least once in 24 rolls of 2 fair dice. So a complement would be no 6,6 appears in the 24 rolls of 2 fair dice. And so if we want to find the probability of A, we simply take 1 minus the probability of A's complement. Well, what's the probability of A's complement? So let's kind of think about it. If we're rolling 2 fair 6-sided die, then we have 6 outcomes for the first die, 6 outcomes for the second die, so there are 36 total outcomes. That seems correct, as stated in the historical document. And the only time that 6,6 can appear, there's only one way that can happen. If I roll a 6 on the first die, a 6 on the second die. So that means for a non-6,6 to appear, there are 35 ways out of those 36 possible outcomes that it can occur. So it would be 35 out of 36 raised to the 24 independent rolls. So there's your probability of A's complement. So the probability of A itself is going to be 1 minus the probability of A complement, which is equal to 1 minus 35 36 raised to the 24th, which I'm not going to write it as a fraction, but its decimal approximation is around 0.4914, which is indeed less than a half. And one thing you might note is that, well, if we calculate it just a little bit different, instead of raising it to the 24th, we raise it to the 25th, so 35 out of 36 raised to the 25th, we get a decimal approximation roughly equal to 0.50555. So it's the 25th roll where the probability changes from, I guess, disadvantageous as a bet to advantageous as a bet. In 25 rolls, you're more likely to see a 6,6 than not, whereas in 24 rolls, it's just a little bit shy of 50%. And this was the thing that really complicated things for Demer. He actually, through experimentation, had determined this result. You note that he doesn't, in his quote, have any sort of numerical representation. So he had a sense that this was happening, was true, but didn't have any way of mathematically, I guess, proving that it was true, and felt like it was a paradox. Well, indeed, it's true, but it's not a paradox at all. And in fact, when we take ratios of, say, I guess, number of rolls to number of outcomes per roll, those things don't necessarily remain constant. And so that's where the misconception seems to lie in this particular conundrum. But the problem was a good enough one to motivate two of the best mathematical thinkers of the day, Fermat and Pascal, and most importantly Pascal, who solves it this way, into the launch of formal probability theory. Lots of what you see on these 2 pages involves the probability theory that we use today to come to conclusions about complicated settings such as this. So there you have it. In July of 1654, probability theory starts to take shape. Let's go ahead. Of course, the other thing that Blaise Pascal is well known for is giving us his Pascal's triangle. And more than discovering it, which he certainly did not, he's given, the triangle is given his name because he really studies it as a mathematical object. And in his triangle arithmetic, published, I actually don't have the date on this. I think it was, here it is, 1654. He he really studies the triangle and gives 19 properties, or what he calls consequences, that can be discovered from the triangle itself. So one of the things he does is he quantifies each one of the, I guess, the locations in the triangle as what we would think of today as defined as a combination. So today we would call this, n choose r is equal to n factorial over n minus r factorial times r factorial. Of course, the factorial notation didn't exist in his day, and he uses just sequences of multiplication to give, I guess, a formal definition. But he's the first one to recognize that there's actually a closed form to find every row and column number in the triangle. Another thing that he gives is some of these consequences, what we would think of today as combinatorial equalities or theorems. And let's take a look at three of them on his famous triangle itself. So maybe I can just switch over and take a look at the triangle, but let's try to get a sense of what's going on here. So the n choose r is equal to go up one row and back, I guess, one column, and then up another row, and in the same column, up another row, same column. That sum is supposedly equal to n choose r. Here we have n choose r equal to n choose r minus n minus r. And the last one, we have 2 to the n is equal to n choose 0, choose 1, choose 2. So it looks like we're summing across a row. So let's go ahead and take a look at how that looks on the triangle itself. So I need to save that. So let's go ahead and talk about first consequence 2. Kind of a complicated one, but the idea here is that, and I'll do it in green here, if I choose, say, a number like 10, then what he says in his theorem is, he says, well, and this would be row 5, column 3, so 5 choose 3 is the same as 4 choose 2, that one, 3 choose 2, that one, 2 choose 2, that one, and 1 choose 2, that one, or excuse me, 1 choose 1. Sorry, and I counted that over 0, 1, 2, so it should be 5 choose 2, so 4 choose 1, 3 choose 1, 2 choose 1, 1 choose 1. But these ones are added together to make that one. So let's see if it's true. 1 plus 2 plus 3 is 6 plus 4 is, yeah, that's 10. So that's what that theorem 2 is stating, is that if you take any column, I guess it's a sort of a parallel column that's one index over and sum it, you'll get that one. Well, let's try it in just a different location and see if it really is true. Let's try, I don't know, say 70. So if I take 70, we're in 8 choose 0, 1, 2, 3, 4. So 8 choose 4. I'm told to go to 7 choose 3. So right here, and then sum all of those columns there that are all in the 3 position. So 1 plus 4 is 5, plus 10 is 15, plus 20 is 35, plus 35 is indeed 70. So all of these sum to equal that. It's pretty interesting. So that's number 2. He gives a combinatorial proof for number 2 using properties that he's developed and definitions. I won't do that here. Let's take a look at consequence number 5. So consequence number 5 says that n choose r is equal to the same thing as n choose n minus r. So why don't we just pick a representative, n choose r. Let's let 15 be our n choose r. So n is 6, 0, 1, 2. So 6 choose 2 would be the same thing as 6 choose 6 minus 2, which is 4. So 0, 1, 2, 3, 4. Oh, indeed it is. Those two are equal. Interesting. Let's see if it's the same thing here for, say, 28. We'd have 8 choose 0, 1, 2, and that would be the same thing as 8 choose 8 minus 2, or 6. 0, 1, 2, 3, 4, 5, 6. Okay. So it looks like all that statement 5 is giving a statement of symmetry in the table. And I think that's exactly what we're seeing here, is that anytime I have a number on this side of, say, the center line of the table, I'm going to have the same number on that side. And you can kind of think of this combinatorially, that you know, the ways that you can choose, say, 2 items from 6. So 2 items from 6 is the same way that you can choose 4 items for 6. All we're doing is excluding 2 items when we're choosing 4 items from 6. So kind of an interesting result. And then the last one in his uh, I guess, the examples I've given you, we'll do this one in yellow. It says that the sum of any one row is a power of 2. So let's take a look at the sum of the rows of the triangle and see if indeed it's true. I'll go down, I guess, 3. Why don't we go through row 6? So if I take the sum of the first row, I can see that maybe over here I'll write in sum. I can see the sum of the first row is just 1. The sum of the second, I guess the 0th row is 1, and that's equal to 2 to the 0. The sum of the first row is 2, and that's equal to 2 to the first. And the sum of the third row is 1 plus 2 plus 3, that's 4. That's equal to 2 squared. The sum of the third row is 6 plus 2 is 8. So that's equal to 2 to the third. The sum of the fourth row is 10 plus 15, 16. So 2 to the fourth. Following the pattern onward, we'd expect this to be 32, 2 to the fifth, sixth row would be 64, 2 to the sixth, and so on. And so it seems like it is indeed true, and this observation is included in Pascal's study of his own triangle. So kind of an interesting set of results there. Consequences 1, 5, and 8. But the one that's probably most notable in Pascal's study of his triangle is consequence 12. Not very, I guess, well known among mathematicians, but what is very interesting in Pascal's presentation is the way that he proves this particular consequence. So let's take a look at his proof and decide just what sort of mathematical idea he's giving birth to through his proof of this particular consequence, I guess is what he's calling them. So maybe what we should do first is take a look at whether or not it's true. What we're told here in consequence 12 is that if I choose 2 consecutive numbers in a row, so let's take something like 21 and 35. So 21 would be 7 choose 2, so, and 35 would be 7 choose 3. So in this setting, what do we have? We have n equal to 7, and r, the first one, would be equal to 2, and this would be r plus 1. And we're told that that if I take 7 choose 3, divide by 7 choose 2, that should be the same thing as n minus r all over r plus 1, which in this case, if we think about what n is 7, so 7 minus r is 2, or 5, so we've got a 5 on top, and r is 2, or 3. So 5 is to 3 as 7 choose 3 is to 7 choose 2, and indeed you can see that's true. 35 to 21 is the same thing as 5 to 3. So it seems like it's working. Let's go ahead and talk a little bit about the proof. Um, so what do we want to show? We want to show that n choose r divided by n choose r plus 1 is equal to r plus a 1 all over n minus r. And so Pascal, the first thing he does is he says, well, for n equal to 1 and r equal to 0, we have the following. We have 1 equal to 1 choose 0 all over 1 choose 1, which is the same thing as 0 plus 1 all over 1 minus 0 or 1. And so it seems like it works for a very basic case, and choose 1 and r choose 0, kind of the smallest case we could. So he says go ahead and assume that this thing is true for some k. So assume that the proposition is true for some n equal to k. So something like this, where we had k choose r all over k choose r plus 1. That would be equal to r plus 1 all over k minus r. Now, if it's true for some value of k, and we've showed it's definitely true for some value of k, in this particular k, then all we need to show is that it's true for the next value. And then that would suffice for sort of a cascade of truth to ensue, that once it's true for the next value beyond some k, then it will always be true for the next value beyond any initial k chosen. And initial k, we've shown it to be true for at least one case. So he claims that what we have to show is that we must show true for the next case, k plus 1, or just k plus 1 choose r all over k plus 1 choose r plus 1 must be true equal to r plus 1 over k plus 1 minus r. Okay, well, we shall see if it is indeed true. Let's go ahead and give it a shot. So how would we do this? We either have to start with this side and squeeze out that side, or start with this side and squeeze out that side. So let's start with the left-hand side, and we'll start with k plus 1 choose r all over k plus 1 choose r plus 1, and talk a little bit about how to solve this. Well, I can see that I'm assuming this to be true. So in order to use this someplace in this proof, I've got to get into a setting where I'm talking about k choose r. And how will I do that? Well, one way we could do it is simply to apply generating function for Pascal's triangle, which is the addition of the two terms above each term. So if I'm talking about the k plus 1 row, well, then I can go back to the kth row quite easily by just adding the two terms that are above this term in Pascal's triangle. So for example, if I'm talking about 21, I could rewrite it as 15 plus 6. This is the k plus 1 row. This would be the kth row. So that's what I'm going to do. I'm going to say that k plus 1 choose r is the same thing as bump it up a row, k choose r plus k choose r minus 1. And then the bottom one I'll rewrite as k choose r plus 1 plus k choose r itself. Okay, so I'm getting a little closer to being able to use what I know to be true, but I really need to write it as a ratio of two combinatorial arguments, or two combinatorial I guess these are binomial coefficients really. So what I'm going to do is I can see I have a k choose r in both the top and the bottom compound fraction. So what I'm going to do is divide both top and bottom by k choose r and see what I get. So if I divide the top and bottom by k choose r, what I get is sort of a mess, but it's going to be on the way to getting us to a solution. We'll get k choose r plus 1, or excuse me, r minus 1 divided by k choose r. That's all on the top. And then if I divide this side by k choose r, I'll get k choose r plus 1 divided by k choose r, and a plus a 1 there. So now I can see that I'm getting really close to being able to use this particular, I guess, assumption that k choose r divided by k choose r plus 1 is equal to this ratio. And in fact, I can see it's exactly equal to the reciprocal of this one right here. So I can plug this in for this reciprocated. So, and then on top, what will I get? I don't know yet, but on bottom I definitely get the reciprocal of that, k minus r all over r plus 1 plus the 1. So now how do I deal with the top? So I can see that it's k choose r minus 1 over k choose r. So the top is a smaller, I guess, choose argument than the bottom, and that's indeed the case here. So it's just simply a switch of variables is what's going on. The index for r has gone down by 1, so I could subtract 1 from r here and here and replace that expression. So if I subtract 1 from r here, I get just simply r. And if I subtract 1 from r here, I get k minus r minus 1, right? Okay, so we're getting close. We want to show this, and we've at least got rid of all the combinatorial binomial coefficient arguments. Now we need to find a common denominator, top and bottom, and try to get this into a fraction form. So let's see, what do I have? On top, I guess what I have is a common denominator of k minus r plus 1. So it'll be k minus r plus 1 plus r all over k minus r plus 1. That's what's on top. And then on bottom, what do I have? Maybe on bottom I'll just write this as a big slash, if you don't mind. On bottom I have a common denominator of r plus 1. So I'll have on top a k minus an r plus r plus 1 all over r plus 1. So top and bottom. Let's do some simplification. I see the r's cancel. I get a k plus 1 all over k minus r plus 1 on top. And on bottom I see that the r's cancel, and I get a k plus 1 all over an r plus 1. And now to divide two compound fractures, I invert and multiply. So this is the same thing as a k plus 1 all over k minus r plus 1. And I would multiply that by r plus 1 all over a k plus 1. And the k plus 1s will cancel. Of course, I'm out of lead right at the critical moment. And I'm left with, let's see, r plus 1 all over k minus r plus 1. And it looks like we have reached our conclusion, which is that this is the same thing as r plus 1 over k plus 1 minus r. And so it is indeed true for the next k plus 1 case. And if that's the case, then it must be true for all. And so I'd invite you to think a little bit about what has Pascal given birth to here through this beautiful argument that this combinatorial result is true. And we'll use that as the launching point of our discussion when I return.